An unknown in the exponent. That's right. If you have an unknown in the exponent, then you're going to take a logarithm. And then what is the change of base formula? So if I had, say, log base A of B, how does the change of base formula work? Andrew? Yeah, log B divided by log A, and then that base is any base you want it to be. You know, it could be 10, so that you can use your log button on your calculator. It could be E, so you can use your ln button on your calculator. It could be 2. The base could be literally anything, and it's still going to end up giving you the correct answer. Okay, so in other words, then how do you type log 530 into your calculator? You just do log 30 divided by log 5. And then what are the 3 ways to solve an exponential equation? What's one way? So what's one way to solve an exponential equation, if you're lucky? What could you do?
Make sure the bases are aligned.
Yeah, you could make the same bases. So you can equate the bases. And then what's the second main way that you can solve it? An exponential or logarithmic equation.
Next one, I would say, is the logarithm.
Right, converting back and forth. So you convert from exponential to log or from log to exponential. And then the last way, which is an expansion of your algebraic abilities. What's the last thing you can do to solve an exponential?
Take the log.
Yeah, take the log of both sides. Any log you want. It can be log base 2, log base 10, log base E. All right. So these are some of our skills that we have. What's that? Wow, that's been up there since Monday. I guess nobody had to use that board, huh? Or if they did, they just worked around it. All right. Oh, that is the backboard. Okay. So today we get to finish up some word problems, everyone's favorite, and then we'll review the practice test, as much of it as we can. So here we are. Today is October 31st, Halloween. We're going to finish up our notes and then do a review, and then you have all weekend to go home, rest, relax, study, and then when you come back on Monday, we'll all take a test. You'll notice I did change the due dates for 3 and 4, so they're not due until next week as well. So all of your online homework is due on Monday the 5th. And as of right now, you could go in anytime, or maybe just on Monday if you need an extension, and you can click the late pass so that you have an extra week to do those. All right, and a joke to start the day. How do you make a tissue dance? Oh, you've probably all heard this one. How do you make a tissue dance? Put a little boogie in it. All right. So we talked about uninhibited growth last time, and did we finish this problem? I don't think we did. I think we started it, but we didn't finish it. Is that right? All right. So let's just review that. We have optimal conditions of lots of food and lots of ability to, well, bacteria, they don't procreate. They just split in half. So they have plenty of food and plenty of opportunity to split in half. And it's modeled by this uninhibited growth formula, which is the number of bacteria at time t is the initial population of bacteria times e to the kt, where k is the constant proportionality. And what did we say? It's been determined that the doubling time is 20 minutes. And so we found the growth constant k. So let's just show that again. If you start with 1,000 bacteria, e to the kt, and keep in mind, e is just a number, so we don't have to solve for it. T is a variable that we are solving for, and k is the constant proportionality, which represents how quickly these bacteria grow. And we want to double the amount of bacteria, so we'll make that 2,000. And then at this point, we're in a position to solve for k, because they told us, hold on a second here, I'm gonna write this down generally. So n of t is equal to that. And then they're telling us that after 20 minutes, so that means 1,000 e to the k times 20, that the population has doubled. Let's just see here. Yes, it's good to double check. It's find a function which gives the number of bacteria after 2 minutes. So we are working in minutes. We don't have to convert it to hours. It's not like when they say 20 minutes, we have to say 20 out of 60 is 1/3 of an hour and then deal with 0.3333. We do get to just deal with minutes, which is nice and convenient. All right, so I have plugged in everything we can to solve for k. I divide out the 1,000. Now I know we did this problem last time. I'm just reviewing, bringing everyone up to speed. So we had 2 equals e to the 20k. And then we want to solve for that k, that unknown in the exponent. So we take a logarithm. I'm going to move my 2 over to the other side. I just prefer to always have my exponential equals a number. So now I know I can take log base e of 2 equals 20k. And log base e is really natural log, so that's natural log 2 equals 20k. And I divide off the 20. And is that the answer we got last time? The k equals natural log 2 over 20? Did we get that last time? Okay. And we might as well go ahead and get a decimal for that. Whatever decimal you get, it's going to be infinitely long. Natural log 2 divided by 20. And we found that k is equal to 0.034657359. Now this is tricky, right? We now have this constant proportionality k. 20. And how many decimals do we need to keep? Yeah, infinitely many of them. Ideally, we'd want infinitely many decimals. You know, if you were doing something important with this number, like calculating your paycheck or calculating how much, what's that called? The stuff that puts you under when you do surgery? Anesthesia. You know, like, do you really want to miscalculate that? You're like, I'm around one decimal. And like, oh, that's my paycheck. Oh, that's my anesthesia. Like, maybe keep all the decimals, right? That's what we're talking about with accuracy, is how important is it that whatever it is that you're doing works. So, all right, so that's k. Now, part B, find a function which gives the number of bacteria after t minutes. Well, that's simple. Now we just write it down. So our function is n of t equals 1,000 e to the very long number 0.034657359 t, right? That's our formula. Now you might say, I don't want to write down all those decimals every time. And if that was the case, you could just change the way you write that, and you could say, hey, I'm just going to write it as e to the natural log 2 over 20 t. Is that any better? I mean, that's what that decimal was. So instead of writing down all those decimals, which aren't even enough decimals because you didn't write down infinitely many of them, why not just write natural log 2 over 20? Because that way, anybody you give this formula to, they're actually getting the right answer. And they can choose for themselves how many decimals to use. All right, so we have our formula, part C. How long until there are 9,000 bacteria? So how do we answer this question? And I know that all of you can do this. Because as you know, in word problems, you can either, they're going to give you a number like 9,000, and you either plug it in or you set it equal to it. So which are we doing? Are we going to plug it in or set it equal to it? Let's keep in mind that the units here is 9,000 bacteria. So would it really make sense to plug 9,000 bacteria in for t? Are we saying 9,000 minutes? No, that would make no sense. So definitely don't plug 9,000 in for t. And this is the kind of thinking you have to do before deciding one way or the other. The units will always tell you what to do with that number. We definitely should set this formula equal to 9,000. So we have our formula, which is 1,000 e to the natural log 2 over 20 t, and we set that equal to 9,000. And now this is just basic algebra. You divide off the 1,000, you take a log of both sides, and we work our way to the answer. So let's divide off 1,000. That's just 9. And so what does that 9 mean anyway? What are we doing to our population? We're non-tupling it. Is that the word, non-tupling? Doubling, tripling, quadrupling, quintupling, sextupling, septupling, octupling, non-tupling, decatupling. There are words for all these things. Isn't it wonderful? So yeah, we're making our population 9 times as big. That's what that number represents. Okay, so now I'm going to put that 9 on the other side because I always prefer to have my constant on the right. And now I take a log of both sides. Well, actually, I just convert to log form. So now this is log base e of 9 equals natural log 2 over 20 t. Keep in mind that ln 2 over 20 is just a fraction sitting in front of the number t. And now I have log base e of 9, that's really natural log 9, equals natural log 2 over 20 all times t. As you look at that, your vision might go blurry and you get a headache. But just keep in mind, natural log 9 is just a number. You type it into your calculator, it's probably 2 something. And then natural log 2 is just a number. You type it in your calculator, it's 0.8 something. So now how do we solve for t? T is being multiplied by a fraction. You know, keep in mind, like, what if the formula was just 5 equals 2/3 t? To get rid of the 2/3, you would multiply by the reciprocal. You could divide off the 2/3, but dividing by a fraction is multiplying by the reciprocal. So you just multiply by the reciprocal. You take this and multiply by 3/2, multiply by 3/2, and that way you get t by itself. So we're going to multiply by the reciprocal. I'm going to multiply by 20 over natural log 2. So I'm over here going to write down 20 over natural log 2. That way, those cancel out and we have our time. Time is equal to, let's rewrite this as 20 natural log 9 over natural log 2. And the thing that is so fantastic about that answer is that it has all infinitely many decimals. If you write down 20 natural log 9 over natural log 2, that has all the decimals wrapped up inside of there, such that when you type it into your calculator, you're going to get the precise answer. You're not going to have any sort of, rounding error in your answer. Your answer is going to be perfect. 20 natural log 9, divide by natural log 2, and we end up with 63.3985. So does it say how much to round? Round your answer to the nearest minute. So 63.4, that means we're just going to round it to what, 63 minutes?
Yes.
This answer is a little creepy, right? Let's say that you eat something that had a bunch of bacteria on it. So there you are, nice and healthy, everything's fine. You're not sick, you don't have any bacteria in your body, but then you eat something and just it's a couple of bacteria in your body, or maybe a few. And then how long until it's non-tupled? Just an hour. So theoretically, when you expose yourself to harmful bacteria, how long until you're infected? Yeah, like not that long, just a couple hours later. Now, how long until you start feeling physical symptoms? Well, I have no idea. But it doesn't take long for, the bacteria to get into your body and then grow out of proportion. All right, great. Well, there's our problem. Now, really, folks, take a look at that. That's some good sophisticated mathematics. What we're doing here is good sophisticated mathematics, giving you the problem-solving skills to solve complex problems. This is fun. Any questions about those? All right, so let's try another one. The law of uninhibited growth also applies to situations where an animal is reintroduced into a suitable environment. Such a case is the reintroduction of wolves to Yellowstone National Park. According to the National Park Service, the wolf population in Yellowstone was 52 in '96. Wow, 52 wolves, that's it. I'm just gonna make a little table of values so we can all see this. So this is the year, and this is the number of wolves. So it was in 1996, there were 52 wolves, and then in 1999, I'm going to skip 97, 98, 1999, and write down 118. Using this data, find a function of the form plank, which models the number of wolves 2 years after 96. So notice what we're saying here is that t is the number of years after 1996. So what is t equal to for the actual year 1996? 0. So that would be 0 years after 96, 1 year after 96, 2 years after 96. 1999 would be 3 years after 96. So it says using this data, find a function of that form. So we would write down our formula, n of t equals n naught e to the kt, which models the number of wolves 2 years after 96. Oh, it even told us, use t equals 0 to represent the year 1996. But hopefully we'd be able to figure that out on our own. Also, round your value of k to 4 decimal places. Oh, now look at that. They want us to round the decimal to 4 decimal places. And if your boss ever said that to you, you'd say, okay, if you want to. I was planning on keeping infinitely many decimals of accuracy, but if you only want 4, right? Okay. So then what? Also random value k to 4 decimal places. According to the model, how many wolves were in Yellowstone in 2002? So there are two things they're asking us to do. First, come up with a formula. And then second, how many wolves will be there in 2002? So that would be the year 2000, 2001, and 2002, which technically represents the t-value 6. Now, folks, you see this little table of values that I made here? I just made that. Right? Nobody told me to make it. The problem didn't tell me to make it. But I just did it because it helps me think more concretely about the problem and to see better what's happening. And so I would encourage all of you to do that type of thing when you're working on problems. Write down more information. You know, help your brain figure out what's happening. And the table of values certainly does that. All right. So what should we do? Yeah, we certainly want to plug something in. The recorded, well, it says the recorded number is 272. That means we're going to use our model to predict, according to the model, how many wolves were in Yellowstone in 2002. They're asking us to figure it out according to the model. They're actually telling us the answer, that in the year 2002, there actually were 272. So we're going to be able to compare reality against the model. So we actually aren't going to plug 272 into anything. 272 is just telling us what really happened, and what we're about to do is predict what would happen. Okay, so what do we do? What do you want to put? Yeah, exactly. This N naught represents how much your initial population was. N naught, that 0, N naught is the initial population. Maybe you want to remind yourself that just in case you've forgotten. So N naught is the initial population. And what do we mean by initial population? We mean how much was there when t equals 0. And when t equals 0, the population was 52. So far we have n of t equals 52 e to the kt. So the initial population is always easy to see by just looking when time is 0. And I want you to notice something about how they gave us this information. They gave us only 2 values in this table of values, right? And we need to use both of them. The first one is telling us our N naught. The second one is telling us a value that we can plug in for t and n of t so that we can solve for k. Because our goal is to solve for k. We need to solve that constant proportionality. So now, if we plug in 3 for t, how many wolves were there after 3 years? 118. That might be worth putting in. There. So you see, we ended up using both of those givens. The first given was just to tell us the initial population, that's N naught. The second thing they told us was to plug in some data so we can solve for k. So now at this point, we just go ahead and solve for k. If you want to rewrite it again, that'd be 118 equals 52 e to the 3k. So what do? We want to solve for k, which is unknown in the exponent. So the first thing we have to do is divide over the 52. Now, dividing over the 52, I don't have a lot of confidence that that's going to be a nice number. 118 divided by 52. Oh, it's this really long decimal. 2.269230769. What should we write down? Just some of those decimals? We should write down all of those decimals. Or better, you can hit the math button and simplify that fraction down to 59/26. We want to hold on to that until the end. So there, all I did so far is just simplify my fraction. I'm not going to write down 2.2692. You notice how they said round your answer to 4 decimals? Well, that doesn't mean that as we go through the problem, we can just round everything to 4 decimals. Because if you round throughout the whole problem, then the last answer is going to be terribly long. You're only allowed to round when you're done. So no rounding yet, so let's keep that fraction. So now what? I'm going to put my number on the right, which I always do. Right? That's how I like to convert logs. So now I have log base e of 5926 equals 3k. So log base e of 5926 equals 3k. All we did right there is just convert from exponential to log form. And then k is being multiplied by 3, so we divide by 3. and that whole thing gets divided by 3. Or if it's nicer to look at, instead of that whole thing divided by 3, you could write 1/3 natural log of 59/26. So what's our constant of proportionality actually equal to? That number. And just so we can all tell how much damage would have been done had we been rounding, let's say that we called the 1/3 0.3333, and then we do the natural log of 59, that was 2.2692. If I compute that answer, 0.3333, natural log of 2.2692, I get 0.2731. Whereas if I do the actual answer, 1 divided by 3, natural log 9/26, I get 0.2731. I was worried that was going to happen. See, sometimes you end up with the same amount of accuracy either way. If you round throughout the problem, you might still end up with the same answer. But that doesn't mean you should round throughout the problem. What if even by rounding, I got this instead of that? That's a huge risk. The 2 instead of a 1 in the 4th decimal place could mean a big difference to you if you're getting surgery or if you're sending a rocket to the moon. Like, that accuracy of that decimal could have made a big difference. So we don't want to round as we go, even though in this particular case it didn't matter. Let's see here. How much did it matter? This was the rounded answer, and this was the actual answer. So you see 0.27311513, and then the actual answer is 0.27311469. So how different was it? It was the 5th decimal place. The rounded answer had a 1, and the actual answer had a 4. So how different were they? Well, it was in the 5th decimal place that they were different. All right, in any case, we're done, right? We have the four decimals, that's what they wanted. K is 0.2731, so now what do we have to do? Yeah, now we're gonna take that K value and make a good formula. So now our good formula is N of T equals 52 e to the 0.2731 T. And that's our model. That's the model that they wanted us to build. They said, hey, all you know is that in 96 there were 52 wolves, and in 99 there were 118 wolves. Let's assume that wolves follow the law of uninhibited growth because they're just making wolf babies as often as they can. And so we come up with a model. Now we have a model to model those wolves. And now we could predict how many wolves there are in 2002. So 2002 is T equals 6. So now we'll just go ahead and plug in how many wolves were there in the 6th year. So that's 52 e to the 0.2731 times 6. And that's just a number. This is just pure computation. This is arithmetic. We just do 52 e to the 0.2731 times 6. And I got the answer 267.69. And you can't have 0.69 of a wolf. So that either means that you're saying 267 or 268 wolves are predicted. How close was that prediction compared to reality? How many wolves were there actually in the year 2002? 272. So not bad. We're off by 5 wolves, 4 or 5 wolves. The model predicted. Why would it be important to be able to model how many wolves there are going to be in the year 2020? You know, if you're the Yellowstone National Park Service, why would you want to know how many wolves there would be in 2020? Yeah. I mean, you might need to take action for that kind of thing. You know, if there's wolves running amok, you might have to maybe put up some fences or maybe capture some wolves and send them somewhere else. I don't know. But you'd want to know so that you can be proactive instead of just waiting until the year 2020 and being like, oh man, we have a lot of wolves. All right. Couple more types of problems that we can model using exponential problems. So far what we've looked at was exponential growth. We looked at the exponential growth of money, whether your interest is being compounded discretely or compounded continuously. We looked at the exponential growth of organisms, whether they're bacteria or wolves. And now we can look at exponential decay of radioactive elements. So radioactive elements such as uranium, plutonium, technetium, all those different radioactive elements, they can all be modeled using radioactive decay, which the formula looks identical. You'll see that the formula looks identical. Let's all make a prediction. If N of T was the number of wolves or bacteria, where N naught was the initial population e to the KT, and now the amount of radioactive substance you have is given by the initial amount times e to the KT. If one of these represents growth and the other one represents decay, what fundamentally is going to be different about these formulas? Right, like N naught and A naught are both going to be positive numbers. Right, like N naught is the number of wolves, so let's say that that's 1,000 wolves. And A naught is the amount of radioactive substance you have. Let's say you have 1,000 grams. So far, we know that N naught and A naught are both going to be positive numbers because they represent how many wolves or substance that you have. So what do you think is going to be different? E is the same number. T is measuring time. Time will also be positive. So what do you think is going to be different about K, provided that one of them is growth and one of them is decay?
Oh, less than 0.
I heard some various voices. What?
Less than 0.
Yeah, one of them that would be positive and one will be negative. So in a growth scenario, K is a positive number, and in a decay scenario, K is a negative number. Oh, and I suppose if we just kept reading, that's exactly what it says, where A at time 0 is A naught is the initial amount, and K is less than 0 is the constant of proportionality. So yeah, K is going to be negative. All right, so we have a problem to do here. It says in exercise 6, here it is, cobalt-60. We list some radioactive isotopes and their associated half-lives. Assume that each decays according to the formula, which we have, where A naught is the initial amount of the material and K is the decay constant. For each isotope, find the decay constant K. So that's what we just did. Round your answer to 4 decimal places again. Which again, I hope I've convinced you all that you're never gonna just round something to 4 decimal places, right? When you hand a number to your clients or you hand a number to somebody, you're gonna get them all infinitely many decimals, right? And then let them make their own choice about how many decimals to keep. Okay, so find a function which gives the amount of the isotope, so just find the formula, and then determine how long it takes for 90% of the material to decay. And then now it says to round your answer to 2 decimal places. Okay, so let's start. First thing it says is to find the decay constant K. So cobalt-60 used in food irradiation. Why are we irradiating food? What food are we irradiating? Any thoughts on why we're irradiating? Is this something you do at home? You're like, hey honey, pick up some cobalt-60, we gotta irradiate this food. Gotta feed the kids. Who's irradiating food? I believe, I don't want to be ignorant here and say something totally wrong, but I believe this is what they're irradiating things like meat. Because if they have a bunch of meat at a factory, and that meat for however long is sitting around at room temperature, they're going to irradiate it to kill all the bacteria that's present inside. Because what's the only other way to kill all the bacteria inside your meat? Cooking, right? I mean, all of you kill the bacteria in your meat by cooking it, right? That's why at restaurants they say, consuming undercooked food is a risk to your health, et cetera, because you could have a lot of bacteria in there. So you cook it. But the meat factory doesn't want to cook all the meat because then all you could ever buy is cooked meat. And a lot of people want to buy raw meat. So the way they make the raw meat safe is they irradiate it with radiation that kills the bacteria. Isn't that crazy? Did you already know that? Did you know that they're irradiating all the meat? That helps to kill the bacteria. Okay, so it's used in food irradiation. The initial amount is 50 grams and the half-life is 5.27 years. So let's take a look at that. We have an initial amount, A naught. Hold on, let's just write down the formula first. That's always helpful. A of T equals A naught E to the KT. It's always helpful to write down the formula first. Because otherwise, how do you even know how to think about the problem? So we know for sure that the initial amount is 50. And they're telling us that the half-life is 5.27 years. What does that even mean? Do you all know what a half-life is? What does that mean, a half-life? Yeah, this is the time period after which half of the substance has already radioactively decayed. So that's how we do it with radioactive substances. We talk about how long it takes for half of it to decay. So it takes 5.27 years for half of that 50 grams to decay. So at the end of 5.27 years, you only have 25 grams left of the substance. And then at the end of another 5.27 years, you only have half of that substance. So if you were just to take a look here and said, okay, this is time and this is amount, at time 0, you have 50 grams of substance. But after 5.27 years, you only have 25 grams of substance. Right? No matter what, even if you just stick it in the closet and you're like, oh, I'm not going to use it, I don't want to waste it. Well, it's going to decay anyway. You can't save radioactive substances. You stick them in a vault, they're decaying in there. So after 5.27 years, you only have 25 grams left. After 10.54 years, you only have 12.5 grams left. And then after, 15.81 years, you only have 6.25 grams left. And then after 21 point something years, you have only 3.125 grams left. So that's how radioactive substances work, is that you figure out how long the half-life is, and then every time that amount of years goes by, the amount of substance that you had just cut in half. So that's what they told us. So now what do we do? What are we trying to do again? We want to solve for K. Now, folks, keep in mind, anytime you want to solve for K, you have to plug in a value for everything else other than K. Anytime you want to solve for a variable, you have to plug in all the other numbers that you can. So what are we going to plug in for A naught? The 50. And now we also have to plug in something for T, and we have to plug in something for the amount. That's the only way that you can solve for K, is to plug in everything else. So what should we plug in for a time value, and what should we plug in for an amount? I wrote out a whole bunch of values. We could use any of these. Right? Any of these coordinates is a valid value that you could plug in for T and amount, because this is T, and this is the amount after that many years. So what would be the easiest coordinate to use? Yeah, probably the first one, because that's why they told us that in the first place. They told us the half-life was 5.27 so that we could plug in 5.27 years for time and put in 25 there. So now here we go, solving for K. What happens when you divide off the 50? What do you get? A half, which makes sense. Because now we're not doubling the population, we're not non-tupling the population, we're halving the population. So again, I'm going to write my 1/2 on the right. That's just how I see it better. So now I have log base E of 1/2 equals 5.27K. So K is being multiplied by 5.27, I divide by 5.27, and this is my answer for K. K is equal to, let's see, that's a natural log of 0.5 all over 5.27. I wrote 0.5 instead of 1/2. Okay, is that what you would have done? So that's our K value. And they said to round that to 4 decimal places. So I'm going to type in natural log 0.5, divided by 5.27, and we get negative 0.1315. It's a negative value, just like we predicted. Because this is a decay situation, our growth of proportionality K value is going to be negative. If you wanted to think more concretely about this, like write some steps down, step 1 would be to write the equation. right? That's always a good starting place. Step 2 would be to plug in your knowns. Plug in your knowns. Oops. And that means in this situation, you plug in your A naught value. We plugged in A naught, which was 50. And you also have to plug in one coordinate. And the one coordinate that you plug in is probably the coordinate they told you about. Like the fact that after 5.27 years, you have half of your substance left. They told you the half-life. When they tell you the half-life, that's actually a coordinate they just told you. But if you plug in 5.27, the function should equal 25. So that's what we did with solve for K. And then you write your model. So see, this first step, we just wrote the equation. It's just an empty equation. It could represent anything in the world. But now that we know our K value, we can actually write down the actual model. And our actual model is A of T equals 50 e to the negative 0.1315 T. And that's the actual model for cobalt. So let's see, how did we do? Part A, find the decay constant. That's what we just did. Find a function which gives the amount of isotope A which remains up to time t. That's what we just did. And now C, determine how long it takes for 90% of the material to decay. So how do we ask that question? 90% of the material is decayed. Do we plug that number in for T, or do we set it equal to? First of all, 90% of material, is that a time? No, so we're definitely not going to plug that in for T. But now we're saying 90% of the material has decayed. So, for instance, we start with 50 grams, and over time, you're going to have less than 50. So,
Percentage of 50.
right. So what do we do then, folks? Let's look at 90% of 50. What's 90% of 50? You can type that into your calculator, 0.9 times 50. Is it 45 grams? 90%, so that's 90% is 0.90. Move the decimal twice to the left. Of 50, you multiply. 9 times 5 is 45. Move the decimal. Yeah, 90% of 50 is 45 grams. So does that mean they're asking, how long do you have to wait until you have 45 grams left? They're saying, how long does it take for 90% of the material to decay?
So you have to minus the 45.
Yeah, so how much has decayed? 45 grams has decayed. How much do you have left? Only 5 grams left. So what we're going to do is this 90% of the material that has, so that means 45 grams decayed. That means you still have 5 grams. That took some careful thinking because we're not plugging 90% anywhere. And in fact, we're not even plugging 45 grams anywhere. We're plugging in 5 grams. That's the amount you have left. So we're plugging that number in for here. You have 5 grams left. You started with 50 grams, and it's decaying according to this model. So everybody, take a look at my handy-dandy table of values I made earlier. Once again, remember, who told me to make a table of values? Nobody. I just did it because it helps me think about the problem. This is a good proactive choice. Make a table of values. Help yourself think about what's happening. So everybody, look at my table of values and tell me, how long do I have to wait? How many years do I have to wait until I have 5 grams left? How long do I have to wait until I have 5 grams left? Where would it be? Right here? So about how many years is that? Anyone take a guess? Should we say 16 years, 17 years, 18 years? Somewhere in that ballpark, 18 years? So we already know the answer. We already know the answer should be around 17 or 18, right? So now let's actually do the problem and see if that bears out. So we've got the 50, we divide out the 50. And so 5 over 50, look how fun this is. We end up with 0.1 equals e to the negative 0.1315. Why do we end up with 0.1? 90% decayed. So how much do we still have? 10%. Right? So 90% decayed, that means we still have 10%, and 0.1 is 10%. So remember, that number that you end up with always represents how much of the initial population you still have. If it's 2, it's doubled. If it's 9, it's not twofold. If it's a half, that means you have half. If it's 0.1, that means you have 10%. All right, so now let's solve for t. Same way we've been doing it. So that's actually 0.1. I take the log, so log base e of 0.1 equals negative 0.1315t. And so then I divide off the negative 0.1315. And we end up with t equals whatever that is. That's natural log of 0.1 over negative 0.1315. So that gives us natural log of 0.1 divided by negative 0.1315. Did anyone else get 17.51 years? Yeah, that's not bad. That's right in the ballpark of what we were guessing. We said 17, 18, somewhere there. It said round your answer to 2 decimal places. So there we go, 17 and a half years. What's the essential process here of what we're doing? What's the first phase of the problem? Yeah, you have to solve for k. Only after you have k do you have a model. And then once you have a model, you can answer any question. You know, you can either plug in for t and say, hey, how much of this substance do I have left? After 20 years, you plug 20 in for t, and then you just calculate it. Or you can say, how long do I have to wait until I only have 5 grams left? And then you plug that in over here, and then you can solve for t. Any questions about that? So there's one more problem right after that. That is about radioactive decay. I think it's the same thing. Yep. Yeah, we'll go ahead and do this one. And then after the radioactive substance, I think there's another type of problem, which is logistic growth. To make sure that we have enough time to do our practice test. So let's go ahead and finish up this radioactive problem. So it says, an unknown radioactive element decays into non-radioactive substances, and after 820 days, the radioactivity of the sample has decreased by 29%. What's interesting about this given is that that's all the information we need in order to create a model for this problem. So how should we begin? You just write down the equation, right? So we have some sort of equation. Well, it's the only equation. A of t is equal to the initial amount, e to the kt. And what we know for sure is that after 820 days, the radioactivity is decreased by 29%. So it's decreased by 29%. So really important. Let's think about it this way. If you have lost 29% of your substance, how much do you still have? If you've lost 29% of the substance, how much do you still have? Yeah, 71%. That's really important. The actual problem, even though people talk about losing a percent, in order to use the formula, you have to talk about how much you still have. So we could say that time, we can plug in for time, which is, what, 820 days? So after 820 days, how much of this A naught do we still have? 71% of it? So we would write down 0.71 of A naught. Now that might look a little funny, because we didn't actually plug in a number for A naught. We don't know how much the initial substance was. They didn't tell us. So all we can really say is that however much you started with, after 820 days, now you only still have 71% of it. So just kind of look at that for a little bit and for it to make sense. We're saying after 820 days, your initial amount has decreased to 71% of the initial amount. You wouldn't put 29% right there, because that would imply that you have 29% of the substance left. But that's not what they said. They said it has decreased by 29%. And if it's decreased by 29%, that means you still have 71%. And so this is what you have. It feels funny because you never plugged in a number for A now. But does it matter that we didn't plug in a number for A now? Can we still solve for K? What's always the first step we do when we solve for K? We divide over that number, whatever it would have been. And what happens when we divide over that number? It just cancels out anyway, and we're left with that number that we've been talking about. That number always represents how much of the substance you have. You know, if you've doubled the amount, that number would be a 2. If you've quintupled the amount, that number would be a 5. We have only 71% of the amount left, so that number is a 0.71. All right, so now we can go ahead and solve for K. Log base E of 0.71 equals 820K. Dividing off 820. That gives us K is equal to natural log 0.71 over 820. So what did anyone get? Your calculator might have given you a strange value to say negative 4.17671108 E negative 4.
Yes.
What does that E negative 4 mean? Yeah, it means scientific notation. I think the E stands for engineering notation. And it just means you have to move the decimal 4 places to the left. And negative 4 means left, positive means to the right. So 4 places to the left, so that'd be 1, 2, 3, 4. And you put in a few zeros. And so our actual answer is negative 0.000417767. So that's our K value. So now that you have your K value, you can actually write down the model, which is D equals some amount E to the negative 0.000417767 T. And that's our model. Now you notice, after I sit up here talking on and on about decimal places, I just went ahead and kept an arbitrary large amount of decimal places, right? I could have written down more. It could have been 671108. And then up here, I could have written down 1108. And maybe that's not even the best thing I could have done. Maybe the best thing I could have done was write A naught E to the natural log 0.71 over 820 T. Because at least that way, all the decimal places are there, and the next person you hand this formula to has all the decimal places. In any case, now what do they want us to do? How long will it take to sample a sample of 100 milligrams to decay to 50 milligrams? Well, what does that mean anyway? If you start with 100, now you're at 50, what are you talking about? You're talking about a half-life. So how long is the half-life of this substance? That's essentially what they're asking. They don't really care about the fact that you're going from 100 to 50. They could just as well be asking, what if you go from 1,000 down to 500? Or if you go from 20 down to 10? It'll be the same answer. Because a half-life is a half-life. No matter how much you start with, you're going to half of it. We're talking about a half-life. So when we plug in, say, 50 right here, and it goes down to 100, and you have E to the natural log 0.71 over 820 T, I could replace this with any two numbers that are twice as big as each other, because what's the first thing you're going to do? Wait, I put those in the wrong order. 50 equals 100. First thing you're going to do is divide off the 100, which is going to leave you with 1/2. So this problem is not really asking specifically about the 100 milligrams and 50 milligrams. They're really asking what's the half-life. In general, how long do you have to wait for half of it to go away? So we have this equation here, and we're going to take or convert it to a log form. So that's log base e of 1/2, which is really 0.5, equals natural log 0.71 over rate 20 times t. And once again, we have t being multiplied by a fraction. How do you get rid of a fraction? Multiplied by the reciprocal. So we're going to multiply both sides by the reciprocal. Oh, reciprocal. So that cancels out, and you have t equals, so what do we have? 820 natural log of 0.5 over natural log of 0.71. When you first start working with logs, you look at 820 natural log of 0.5 over natural log of 0.71, and it hurts a little bit, right? You don't look at that number and think, oh, yeah, sure, that much. But I hope that you all appreciate that by writing down the number in that way, you have infinitely many decimals of accuracy. And now if you wanted to, if you just had some casual end user and they're like, hey, just roughly speaking, how much is that? Then you could type in 820 natural log 0.5 divided by natural log 0.71. And you could casually say, oh, 1,659.55 days. That's the half-life. By the way, is that answer reasonable? Make a table of values. We have time and then amount. And at time 0, we have 100% of a substance. And they told us that at time 820 days, we only have 71% of the substance. And now they're telling us that after 1,659 days, we have 50% of the substance. So does that seem plausible? If you were to look at that table of values, would you say, sure, I believe it? Because after all, that's 820 times 2 would be roughly 1,600 days. So you've doubled that amount of time. And sure enough, the percentage continues to decrease. So, yeah, that looks like a reasonable answer. Yep, word problems with exponentials and logarithms. Were those fun? You're like, oh boy, yeah, this was great. Well, folks, here's what I think we'll do, because I'd like us to be able to have the second half of class. I know that there was this last question about modeling logistics, and these are very interesting, and this is fun. But I think for the sake of time, we can skip this one. So you can cross out that page, and then this one. Yeah, we'll loop those problems back into some other chapter, and I won't put it on the test, and it's not on the practice test. So the rest of those problems we're not going to do for this test. All right, yes?
Are the ones that were crossing out?
No, they won't be on more. I'll go ahead and delete them. They will be in your dreams, however. You can't delete them from there. All right, so folks, before we look at the practice test, I need everyone to come on up and sign up for some. I remember last time I took a picture of all the people who hadn't gotten to go. So I went ahead and pre-populated your names if you were on the previous list. These are all the people who didn't get to go last time. Speak out or forever hold your peace. Did you go last time and I wrote your name on the list? I don't think so. What, you did, you already said? No, okay, yeah. So this was everybody who didn't get to go from last time. I've already filled you in for chapter 5. I need one more person to sign up for number 10. And then I need the rest of you to sign up for chapter 6. So if your name's already up here, you don't have to come up. If your name's not already up here, come on up and sign up for a problem. And of course, if I signed you up for a problem that you're not sure how to do, then while I'm walking around the room, go ahead and ask me, like, hey, Mr. G, how do I solve this problem? Because I'm about to go and write it on the board. Yeah, that's number 9. Yeah, you can do number 9. No, by all means. And otherwise, we'll go ahead and take our break. I'm also giving you time to sign up for a problem. So let's just say to come back at 9:10. That's right. Of course.
Is one of the questions you eliminated on the chapter, on the practice?
No.
And the other question is, do we have to know the formulas while you're assigning us
I could put those on the test.
a revision?
Yeah, that's fine. There's only a couple.
Mister, are you having office hours?
Yep, every day. Yeah, every day right after class.
Oh my gosh. Why do I keep doing that?
Good to see you too.
Straight right there.
He's a teacher. I guess. Sorry about it. One of the questions I didn't have negative answer.
Uh-huh.
The last one. Oh, yeah.
Oh, the practice test? Okay, well, let's see. Decreases by 51%, but you keep 49%, and you wrote 7. Right, is that it? Yeah, because you put in separate. Oh, no. Okay. So, but, oh, yeah, that's what it is. That should be. Yeah, so that should be 0.49. Because you're talking about how much you still have.
Thank you.
Sure.
All right, folks, let's keep going. So at this point, we have just over an hour to review this practice test. I'm going to walk around the room and help each of you individually. So when I get to you, I hope you have a question you'd like to ask me about the practice test. You've had the practice test for about a week now. You've had the solutions. Hopefully, you've already worked your way through it, and you know which questions you have and what you'd like to ask me. We're going to start by having the first people come up to answer the question from chapter 5. That was a couple weeks ago that we did this, so this will be a nice review to get you back in the mindset. And by the end of the class, we'll be getting towards the problems that we just basically did. So we might not actually get to the last problems on the practice test because we did, after all, just do those problems at the beginning of the hour, but we'll see how far we can get. So let's go ahead and get started. I broke down some of these problems into part A, part B. I hope it's obvious what part A and part B is. You know, there's two parts to the problem. So let's go ahead and have Yaritza, Oscar, Erica, and Tanya come on up and do all the parts of number 1 and 2. I realize I don't want you standing on a chair to come up here, so maybe just write down your problems down below somewhere. So Yaritza, Oscar, Erica, Tanya. And there are 4 markers up here. Otherwise, I'm just going to walk around the room to help. If you have questions, I hope that you ask me. You can work with your neighbor. And I'm going to start the back. Wait a minute. Yes. Oh, what is it? Oh, you see right now. Oh yeah, you can see it like this. All right. Oh, this is good. See, I'm not worried about yeah. Yeah, it is true. That's so crazy. So that guy is. I also know that I was even making sure someone said wow, I'm pretty sure they'll go crazy. It's not like, how up was it? That's like crazy. I didn't even think about that. That's like the first time I heard the joke. I'm like, it's not the extra automatic thing. What we want to say is, first of all, we have 2 things that we have. The denominator can't be 0. So that whole thing, root x squared minus 4 can't be 0. So that can't be 0 because that's the denominator. So then I square both sides. Now I know x squared minus 4 can't be 0. And then I have to the other side, I know x squared can't be 4. And therefore I know that x can't be 0. Now that's one restriction. The other restriction is you can't square the number. Now I know that x squared minus 4 has to be actually bigger than or equal to 0. Because you can square root to 0 and you square the opposite. So now I have this restriction, x squared is greater than 4, and that you have to look on the graph. And you also see that this parabola has to be on the x-axis. So x squared minus 4 is not that, and that's you look at a graph and calculator, see that graph. So x squared minus 4 is greater than 0, you get this way. So now I'm in another one. I say, well, it can't be 2 or negative. It's this zero. And then another one not. And so I'm going to do it that way. So really, the devil is more work to work down. I concretely just thinking, okay, I can't divide by 0. So all of that is can't square a negative. So I put that back in. And then make another one, divide by 0. Because I could still make that doing all these things. So we have a variety of long remedies. One of which is long A plus long B. You're gonna have all these log properties memorized, at least written down somewhere where you can see it. So it's log one. Product. Right, so that's what we're gonna do here. We're gonna say, well, you're gonna keep the log stays there. But then on the inside of that log, we have X times it. Right, and that's still equal. Well, it is about the matter, so I'm gonna put it in right there. So now, since they gave me a logarithmic expression, I can convert it. So that was a 10 to 1 equals X. 10 to 1 equals X. And now I can convert it from a logarithmic expression to an exponential expression, and this is basically 1%. Well, we're gonna distribute those. Oh, so now we have X squared plus 5X. I'm going to move from 10 to the other side. And minus 10, and all that equals 0. So like this. And that is not factored. Something more comes from 10 and 5. See that these are total. Is that total? Yeah. Okay. Can you see everything that I just wrote there? Then you know. No. That's easy. Well, why is it gonna just open that one?
Well, no.
Oh, I see, so I shouldn't have written it, because that was. Okay, well.
Yeah,
it's so close together.
Yeah. But he was just looking over there.
Oh.
Yeah.
I gotcha. Oh, okay, and that's, that wasn't there? Yeah. Okay, and so, yeah, now this part of it.
Yeah.
Oh, okay. So, and the first thing we're gonna look at is the inside. The evaluation of the inside. So what's G of null? So this is my G of null. This is my X values. So you're basically going like that. So G of 1 is 4. So now you know that G of 1 is 4, and now that's the input in the next function F. So you go to F column, you go to 4 column. Now F 4. Now really important, use your fingers to do that. Like when you're doing G of 1, put one finger up here, put one finger over here, and actually you make your fingers put together physically so that your eyeballs don't do the same thing. It really helps to make your fingers do it because they can eyeballs. Okay, so try it. One finger up here, and the other finger over here pointing at it sideways, and then put them together. So that's how you do it. So try a couple more. Okay. For the inverse one. Yeah. Okay. So if it's F is 3, well, that's easy. It means you're plugging 3 over there. So 3 is the input, therefore 6 is the output. Yeah. So for this sense, for the inverse, you switch the order of inputs and outputs. So the number going into this inverse is no longer an input of 6. Now we're plugging the 6 into the output. Right? So you plug the output in, what input you get. If you're switching the order of input. You're always just looking at variables. So like this one, if the inverse is 6, so again, you're plugging in this number, you're plugging in an output to get an input. So I'm looking at my input, and therefore, all right, let's take a look at the first couple. Number 1 was done by Yaritza. Thank you, Yaritza. Was that up here, f of g of x? Is that this one? So f of g of x. So then you got something squared minus 3 something, and then you plugged in x plus 7. And then you just FOIL that out, and then you subtract it, combine like terms, you factored, and then you got negative 4, negative 11. Now, this was going beyond the call of duty. Everybody take a look at what Yaritza did. Once Yaritza gets to here, or to here, she's actually done. That is what f of g of x equals. right? So this problem didn't say to set it equal to 0 and solve, but yet if you said set it equal to 0 and solve, find the x-intercepts, then you would also be able to say that the x-intercepts are -4 and -11. But nobody asked for the x-intercepts. They just wanted to know what the function was. So you could just say the answer is x squared plus 11, x plus 28, or factoring it is very nice because that does precede, to tell you the x-intercepts. It's just that this problem didn't ask for it, but you went above and beyond. Okay, and then that was Yaritza. The next one was Oscar, number G of f of x. So Oscar is plugging in the x squared minus 3x into the x plus 7. And Oscar, I believe you have the right answer. I'm just going to write it out a little bigger so everyone can for sure see it. We're doing the g function first, which is something plus 7. And what are we plugging into that g function? The f function, which is x squared minus 3x. So yeah, it's the same exact answer. Just want to make sure everyone saw why you plugged it in that way. But I like how your little arrow, you're saying, hey, just take that whole thing and plug it in for that x. So yeah, that's a good way to visualize it. All right, thank you, Oscar. Thank you, Yaritza. How about number 2? A, that was done by Erica. So Erica is going to find the domain of p of x over g of x. So p of x is 1 over root x, and g of x is x squared minus 4. And we want to divide those two things. So first of all, notice what Yaritza did. Sorry, Yaritza. Erica actually just took those two things and divided them, and she ended up with 1 over root x times x squared minus 4. So now you have two domain restrictions, right? What are the two things you have to look at with domain? What can't you do? You can't divide by 0, and you can't square root a negative. So the first thing she said was, well, first she factored that. The first thing she said was this whole thing can't equal 0. So she knew that root x couldn't equal 0, therefore x couldn't equal 0. X minus 2 couldn't equal 0, therefore x couldn't equal 2. And x plus 2 couldn't equal 0, so x couldn't equal -2. So she has these 3 restrictions so far, which she put on the number line. Now, there's one more thing you have to do. And I don't necessarily see your work up here for it. Erica, you can't divide by 0. What else can't you do? You can't square root. You can't square root negative. So therefore, you know that this x right here, remember the radicand, you always take the radicand of the square root and you just say, hey, that thing has to be greater than or equal to 0. So Erica took her number line where all she knew so far was that it couldn't be -2 or 0 or 2. But now she also knows that it has to be a bigger than 0. So she shades to the right. And that's why she shaded to the right. And she ends up with this picture. Now notice, folks, the radicand alone said that x had to be bigger than or equal to 0. But we already know it can't be 0. So it just means that it has to be bigger than 0. So that's the part that could be a solution. And so therefore, her domain is 0 to 2 and 2 to infinity. Folks, I know I do it all the time up here. I really recommend you draw this number line. The number line helps you make concrete what you're doing with your domain. Okay, thanks, Erica. So then we have Tanya. So the domain of this fella, she first had to find p of g of x. So p of g of x. How did you figure that out? So p of g of x. You look at the outside function first. So p is 1 over the square root of something. Wait, did I just do that right? Yeah. And then you're plugging g into it, so you're plugging in x squared minus 4. So now Tanya has the same question. Her denominator can't be 0, so she takes the entire denominator and says, hey, that can't be 0. So she squares both sides, get x squared minus 4 can't be 0. Moves the 4 over, x squared can't be 4, and then square roots both sides, x can't be plus or minus 2. So on her number line, she just has plus or minus 2 here, which it can't be. Now that just means the denominator can't be 0. She also now has to make sure the radicand is positive. So now she takes the radicand, which is x squared minus 4, and says, hey, that thing had better be greater than or equal to 0. And at that point, what did you do, Tanya?
I drew the graph.
Yeah, you draw the graph. Exactly, because this is a parabola, it has to be above the x-axis. So she looked at her graphing calculator, saw that this is where it's above the x-axis, pointing to the left and pointing to the right. And so on her number line, she shaded to the left and shaded to the right. And that's it. So the left-hand interval is negative infinity to -2, union 2 to infinity. Which those are really good questions. And I just want to remind everybody right now, because, I mean, each of those is a fairly long chain of thought. And if you're sitting at home, you know, you've got the weekend, you're going to go home, Finally print out that practice test in case you haven't printed it out. And just remember, you can go right into more. This was the practice test for chapter 5. So watch, I go to module 5, I go down to optional practice test, and then from within there, I just have to scroll down until I find this problem. So this was the domain of p of x and g of x. So I'm just going to go ahead and start clicking down here. Domain. Oh, there we go. The domain of blank. So they're saying the domain of f of g is equal to, and so here's a problem that looks pretty similar to this one. And you can go ahead and click on the video and it will show it on the video. So just keep in mind when you're sitting at home and you're not sure how to do a particular problem, all of these problems are in the practice test, which means there's a video that's going to walk you right through the solution. So I hope that you use that as a resource. And then again, of course, you can also just look at my solution, because I posted a solution to all of these online as well. And then, of course, you can email me. You're sitting at home, you watch the video, you look at my solutions, you still don't know, email me. And I will email you back on the same day. Okie doke. Thank you very much. I think that solves, or that finishes those problems. So now we're on to 3A and B. So Jennifer and Drea. Come on up. And I'm going to keep walking around the room and help everybody. The people who are coming up, if you would always erase before writing down your solution. No, where was it? Okay. That's what so this is the practice test. Okay. Well, here, let me go ahead and give it a second. So f of x, let's just say is root x. And g of x, let's just say is x squared minus 3. Yeah. Okay. All right. So no, I have to do it. Yeah, that is what you're doing. Just plug it in. And so, like, for instance, the way the model on the board, you would say, okay, that's f of g of x. And so first I write down the structure of f, which is just the big square root. And then what do I plug into it? I plug in g of x, and I plug into it. So that would be f of g of x. If I wanted g of x. Then I would write down the structure of g first. So now the structure of g is something squared minus 3. So I go something squared minus 3. That's the structure of g. And then what do I plug into it? I plug in f of x, which is x. And then this one simplifies a little bit. The square root, just get x. 5. So those are my different solutions. Okay. Okay, let me know if you have another question. Oh. This is okay. Well, we're converting on log form to exponential. Yes. So anytime you have something like that's exponential form. And then if I convert it to log form, it's log base 2. So the first one log is 2. And then log is
I mean, I don't know.
so this process converting actually into log form. That's what happens.
But if you don't.
So this logarithm really, remember what it says 5 to the what?
Maybe you didn't.
So 5 to the what?
My,
And they're actually
we tried with my factor.
5 to the -2 is left to right. That's what they say. Left to right. Yeah. So that's left to right. Also 5 to the 3. Naturally left. That's a good question. Yeah, that's an interesting way of saying it. A lot goes away because And then back to the switch to H. So the log represents the x goes to minus x squared. So since we switch the number back, I'm gonna have to find another one.
I noticed that this is what to know.
Okay, anyone? Answer the question, right? Oh, sir. That's right. Yeah, you know what, that's a really good question. A lot of people do it in a lot of different ways. The most careful way, most is to just follow along. So that's- Oh, yeah, that's- Yeah, very nice. So your answer is natural log 4/3, and then from that you subtract 1, and then from the whole thing you're dividing by 2, right? So certainly one thing you could do is you want to take natural log of 1/3, so that's what that is. Now this correct that. That's what that is. Divided by 2. That's what that is. If you wanted to do it all at once, remember your numerator always has to go its own parentheses. So you have numerator parentheses, and then natural log of 4/3 minus 1 numerator parentheses, and then add you should get the sentence. What would happen if you didn't add the numerator parentheses? So the numerator parentheses is really important. Do you have another question? You know, well, yeah, certainly, and you know what, so, right, yeah, so you're saying 2 to the 1 is 1, and the exponent is certainly negative, and in this case, it has to be. And you know it has to be because it's reciprocal. Yeah. Two to the x equals 2 to the x, exactly, and that was. Okay. Four is 2 squared. Perfect. Right, you multiply it out, so you just. So, domain, one thing we can do is graph it. Oh, I see, you're actually graphing it yourself. That's a little tricky. You have a graphing calculator. So you could go ahead and just. So where does the graph begin? Okay, it looks like it starts around there, and then it moves to the right. So already we know the domain starts around the end of 1 and moves to the right. So there's no graph over here, so that's not part of it. So the domain is going to be something like how far, domain is how far left and right. So the graph goes left to that point and then right over to that point. So we already know that the answer is going to be something up to the positive. Because the graph appears to be right. So the only question is, what is that? And it would be tough to use, well, it would be more like that is 0.6. But the thing with that is it's going to be perfectly exact. So the main thing we need to know is just like with the other domain questions, one thing you're not allowed to do, you're not allowed to square root and you're not allowed to long. In fact, I don't even think we can use this. Just try it. Go ahead and just add it long. Nope. So you can divide by 0. Not square root of negative, and you can't log as 0 or 1. So what are our restrictions? That means that the denominator can't equal 0. That's one. The radicand, we use part of the radicand, has to be greater than or equal to 0. Because you can't square root of 0, and you can't square root positive. So the radicand has to be that. And then the log can't log a negative or a 0. So you have to strictly log the argument. It has to be strictly given. So what that tells us is that this has to be strictly given. So 4 plus 6x has to be greater. You can only log the positive. How's that simple? Okay, these are your 3 domain restrictions. So now we just subtract out the 4, so now 6x has to be greater than 4. Divide out 6, x has to be greater than negative 6. And negative 4, 6 is really negative 2/3, which is negative 4. 6, 6, 6, 6, 6, 6, 6. Which, go back to your table. You can tell that we were getting close to it. Oh, it's because the total skips over between 0 and negative 1. So you change your table value, but you're actually getting set. And you can change the increment of your table to 0.1. Then, oh, yeah, okay. Now you can actually see. Yeah. So you still had a value up to negative 1.6, but then as you switched over to negative 1.7, you don't have it. So this all just confirms that negative 1.6 is the last endpoint. Does that answer your question? Okay, because that's it. So my number line would be that sorry, and I am technically excluding that number, and I can choose any number. And that's what graph is. Any number on the right. Good question. I'll be right back. All right, folks, let's review these questions real quick. Number 3A was done by Jennifer. 3A, she had to evaluate a few different numbers. So I like how she did it, how she set it up. The first one, it was G of 4. So it's F of G of 4. So everybody remember, this type of problem, you want to look up on the graph and use your fingers. So G of 4, I would go to the graph of G, input 4, output 1. So that's why she went from G of 4 to 1. Now F of 1, I go to the graph of F, and I input 1, and the output is 0. So that's that one. Really nice, Jennifer. And then for the next one, G of F of 5, so go to the F graph, input 5, output 4. So now she has G of 4. Go to the G graph, input 4, output 1. So that's what she got. F of 0, she inputs the 0 to get 5, and then takes that number 5, inputs it again, and gets 4. So that's correct. And then G of 3, she inputs 3 to get 2, and then inputs 2 to get 3. And that's it. Thanks, Jennifer. How about the next one? Drea, 3B. Okay. Oh, yeah, so same thing, using the table of values is what Drea did. So here she did G of 1 first. So, folks, again, you probably want to use your fingers here. If you want to solve G of 1, you're looking at the G column. The input is 1, so the answer is 4. So G of 1 is 4. And then F of 4, you look at the F column, input 4, answer is 9. And that's what Drea got. Okay, I don't think I'll go through the rest of those. If you have any questions, let me know. Thank you, Drea. Thank you, Jennifer. By the way, were all those correct?
Yes.
They were all correct? Okay. All right. Next couple of excited people, 4, 5, 6. So, fun, Alexis, Manuel. Jonathan. So, what number is it? We'll bring that over here. Okay, so 11. Computer purchase for $11.50 loses 10% of its value every year. Right, exactly right. And so according to the model, there we go. Where V is the value and T is the year since purchase. And then so in this, I don't think we actually did a problem with this in class. A is the initial value and B is the Q. And I should tell that to everybody. So A is the initial value and B is the percent Q. So I would write that down. A is the initial value, B is the percent Q. And I'll definitely have to say that. All right. So in that case, then, The initial value was 1150. And then the keep amount was 90%. And that's it, that's the whole formula. Let's see your calculator. The reason this makes a lot of sense is because if you're starting with 1150, so that's how much I start with. Then after every year, I only keep 90% of it. So I'm going to take that and multiply it times 0.9. So I've multiplied by 0.9 once, and now I only have 1,035. So I only kept 90%. If I hit times 0.9 again, so this is the second year, now I only still have $934. And every time I multiply by 0.9, I keep decreasing. And that's exactly what this formula suggests, is that 0.9 is being raised with an exponent. So let's say, exactly. So let's say that I wanted 5 years to go by. That's really 1150 times 0.9, 5 times. So you have to do 1150 times 0.9 once, twice, 3, 4, 5 times, and that's how much 9 is. So that's it. And so then what, in the actual problem, how many years until it's half the value? So you set it up by saying you have your formula, and you're setting it equal to half of the 1150. That's what I did there. I took my equation and set it equal to half of the 1150. On the plastic, so far we were actually replacing the V of t with half of 1150, which is 575. So another way to have done it would have been to set 575 equal to 1150, and then go on. So you can try that either way. Now make sure you write 1150 times parenthesis 0.9 for the t. Another one? Okay, go ahead and do that problem and then I'll come back. Annabelle? Hey, did that other problem work out? Oh boy, I wonder if I did that whole problem wrong. What is that? Yeah, well, hold on a second. See, oh, and you know why? Because I'm doing this problem using the other model. There's 2 different ways of doing it. Silly me. The other model was this one. We have a times b to the t. So did we get the same answer? No, but what your final answer was 323.8, and your final answer was 323.8. Yeah. To get your K value. Yeah, that's fine.
So I did that. And you clarified the answer.
Yeah.
So I got the answer, but that was only section.
Yeah, so we still need to find the half-life. And
like, my question is, but I have to use that one.
yeah, exactly. And I used it because I saw it earlier in this one.
This one, and that was another one.
Yeah, and you know what? I just was helping Jonathan with this, and I realized I hadn't done it. So I definitely need to do 11 and 16 with you folks today, so that you can see. Now this one you can still do it your way. You don't have to do it my way at all, because now I can still find the half-life. What's the half-life? I just set, whatever A naught is, you set the other side equal to 1/2 A naught. You have to solve it. Let me do it on the board, and that way everybody gets to see it. All right, let's go ahead and review these next couple of problems. And what were those? Annabelle, 11 and what?
11 and 16.
Okay. Okay, so moving on then, we had 4 was Juan. So number 4, use the table to fill in the missing values. So take a look, because this one is a little tricky. You need to remind yourself that a function goes input, output, but an inverse goes output, input. Remember, an inverse switches the order of input and output. So for f of 3, 3 is the input. So if it helps on these columns, x and f of x, you could call it, input, output. Oh, not quite far enough. So there. So that's my input, that's my output. So when I'm looking at the function f of 3, my input is 3, so my output is 6. And that's why 1 is the answer of 6. And then he's saying f of what input will give me an output of 7. So I find the output of 7, and therefore the input was 6. So that's 6. Now they're asking about the function. I'm sorry, the inverse function. And the inverse function switches the order of input and output. So now when I say f inverse of 6, 6 is no longer the input. 6 is now the output. So now I look over here in the output column to find the 6, and I say, well, what input is associated with that? That would be the 3. Because it's switching the order of input and output. So now when you're plugging something into F inverse, you're actually plugging in the output number. So if you plug in 6, it gives you a 3, and that's that. Likewise, if you're saying, what would I have to plug into the inverse function to get 6? That means x is the output value. It's associated with the input value of 6. So I go to my input value of 6, and that's associated with the output value of 7. So if I plug the output 7 into the inverse, I should get the inverse 6, and that's why the answer is 7. So it switches input and output. Thank you very much, 1. And B, I'm sorry, 5 was done by Alexis. Where's oh, she's not here. Oh, still with me. Okay, let's do 5. So number 5, it says, let f of x be x plus 9 squared, find the inverse. Well, remember the steps, folks. You replace f of x with y, and then you switch x and y, and then you just go about solving for y. So y is being added by 9 and squared, so I would square root both sides. That gives me y plus 9 is equal to the square root of x. And then y is being added by 9, so I subtract by 9. And that gives me y equals root x minus 9. And that's the inverse. Oh, and then finally, I replace y with f of inverse. So f inverse of x is root x minus 9. Notice that in a problem like this, you can check your work by thinking about the story of x. The story of x here is that x is being added by 9 and then squared. So if I go backwards and reverse, I would square root and then subtract 9. And therefore, my inverse, f inverse, is going to be that I take my x, I square root it, and then I subtract 9. And that gives me the same answer that I got. Since you're inverse, you don't have to do anything else with it. Just find the inverse function. Okay, number 6 was done way over here. Manuel, thank you, Manuel. So you had f of x. So follow along with Manuel's steps. You had f of x was this. He called it y equals x plus 1 over x plus 9. You replaced y. Oh, no, you switched the x and the y, right? Is that what you did? You switched the x and y? Yes, you did. So you switched the x and the y. You wanted to get rid of your denominator, so you multiplied it over. So then you had a distribution of x times y plus 9. So you had xy plus 9x equals y plus 1. He wanted to get all of his y terms to the left, so he brought the y term to the left. And then he moved his number term. Is that plus 9x right there? So he moved the 9x over to the other side by subtracting. So then he had y times x minus 1 equals 1 minus 9x, and then he divided off the x minus 1, and that's it. So you got it, Manuel. So y is equal to, or f inverse is 1 minus 9x over x minus 1. Folks, I'll just tell you that a problem like this is not just on this test. A problem like this is on your final as well. This is a good problem to do on your final, because this problem is too easy to go on the final exam. Find the inverse of a quadratic. This is too easy. What's that? Oh, you like that one? Yeah. Whereas this is a good, meaty, lengthy problem where you have to first cancel the denominator and then combine like terms, moving your y terms to the left and your non-y terms to the right, and then factor out a y and then divide it off. This is a great problem. So essentially, you should go home and practice this problem until you can do it without looking. I don't mean do it without looking. I mean do it without looking at your notes. Okay, thank you very much, Manuel. Let's move on to the next couple problems. 7, 8, and 9. So Jackie, Annabelle, and Michael. Oh, well, I think I'm about to get there anyway. I'm going to finish this part of it, and then I'll go back to those questions. Isis. Okay, we'll do that all together. Oh, okay, yeah. I tell you what, you don't have to use 4 thirds. You can use 1.33, so long as you use infinitely many threes. Lots of threes.
Okay.
Like at least 10 threes. Typically, if I'm gonna use a decimal instead of a fraction, I mean, see, like, take a look. If you did 4/3, it's just a matter of wrapping in parentheses. So you say 4 divided by 3, and if you wrap that in parentheses, that is the number that you did put. Or if you want to use 1.333, I typically use as many 3s as it takes to fill the entire screen and wrap to the next. If I fill the entire row and wrap to the next, then I feel pretty confident that my level of accuracy is going to be there. Yeah. Oh, well then the other thing is that when you do this, you need a parenthesis around the entire numerator. That's going to make the difference right there. You need parentheses around the entire numerator because otherwise you're calculating things, you're saying natural log 1.23 minus 1/2. You're not doing 1/2, you're doing the whole thing divided by 2. So you need parentheses around the entire numerator. That's okay. Yeah, that is the right answer. Yeah, but if you type it out all in at once, like you type natural log 1.23 minus 1 divided by 2, that's going to be wrong because I don't have a parenthesis wrapping around the entire numerator. And unfortunately, that's what some of these do is they'll just type it out as they see it. Natural log minus 1 divided by 2. And now that answer is incorrect. Whereas if you put a parenthesis around the entire numerator. Okay, so now do you see there's a parenthesis around the entire numerator? Now then. Oh wait, that's not the same answer. What did I do? Natural log 1.3333 minus 1. Oh, because I don't have a parentheses ending my natural log. So I need to end my natural log so that my calculator knows that there, now it's just the natural log of 1.3 and then minus 1 and then divide by 2. And now my answer is the second source. Oh, so many parentheses. Actually. So remember, you're not allowed to divide by 0, and you're not allowed to square a negative, and you can only log a positive number. So 4 plus 6x must be greater than 0. So you just write down 4 plus 6x greater than 0. Nope, don't have to do anything like that. You just need to, just like the other domain things. Can't divide by 0, can't square the negative, can't log. Well, you can only log positive. So you would just write down 4 plus 6x greater than 0, and it's all for x.
Okay.
And then make a number line, write it down. Anyway. All right. One question. So this is a classic log problem where the main thing you want to think about when you see a log or an exponential is convert to the other form. So if they give you a log, convert it to exponential. If they give you exponential, convert it to log. That's pretty much always the one. So in this case, how do we convert this into exponential? You'll have an exponent. And what we talked about in class is that it's left to the right. So this is really saying, sure, you can. I mean, it's going to be 2 to the 5 equals 4 plus 4. Remember how to read this. This states 2 to the what is 4. 2 to the what is 4 plus 4. That's what this is asking. 2 to the what is 4 plus 4. And this is actually giving you the answer. It's 2 to the 5 is equal to 4. And so that's why we say it's left to the right. So just go ahead and write down 2 to the 5 is 4. And that's converting it to 1. At that point, just back to the calculator. Oh, well, that's fine. Sure, sure. I mean, one way to think about it is you're saying 2 to the 5 is equal to 4. It's just that, yeah. Yep, yep. Exactly. Okay. Oh, great. Okay, so one thing I didn't do is put parentheses around the entire numerator. When you're writing an answer, you don't have to put parentheses. But when you type it in, you need parentheses. So just notice how many mistakes you have. Like if I just type natural log, 4, and And then I write minus this, and then I write 2. That's all wrong. Because there's no parentheses.
That's why.
So, and plus, it's whatever that is. So what I really need is parentheses. You say, okay, my numerator consists of natural log, and those parentheses to say what's in the natural log. That parentheses ends in this. So now, so far my numerator, I have natural log. Then I'm going to subtract 1. And now that's the end of my numerator. So I close with parentheses. So now I have my entire numerator. Now I divide by 2. Now I have parentheses. Anyway, no. Yeah, because yeah, I'll come back. Okay. Okay. So
What you got?
you've got y equals, and this is the one that's still on code. So, first one, you can always look at my solutions. So, first, what's the first step? Go ahead, do it. And you're gonna need a y plus. So x equals y plus 1 over y. And we want to solve for y. So the fact that we have a fraction, the denominator is very convenient. The first thing I have to do is get rid of it.
Oh, that's.
Yeah, multiply both sides by the denominator. Because that way it cancels on the right hand side. So you can write it as cancel. Exactly. Yeah, so now you have y plus 9 times x equals y plus 2. And this is just me. I always like to see it distributing over. Because that way I can see myself distributing. So now go to
Yeah, but I'm just.
now remember our goal. Our goal is to solve for y. Our goal is to solve for y. So that means we need to put all of our y's on the left and anything else on the right. Yeah. No, that's 1 minus 9x equals. Combine those. So it's still just y plus 1 minus 9x. Now you can move that y to the other side. We're just going to write minus y. That's the important thing about algebra. Don't think about it. Just write it down. So now that cancels. So now you have xy minus y. And you just write it down. Y minus y. Equals 1 minus 9x. Now at this point, there's a y in both of those. That's technically 1 y. Xy minus 1 y. Back to the y. So then you have y in front of x minus y. Equals 1 minus 9. Now you're almost done isolating y. Y is being multiplied by x minus 1. So you divide that.
That's why.
You're just dividing both sides. And it does, because that cancels it out. There you go. So y equals that. And so this y is actually the inverse. So you write f inverse. You did it. That's good. Oh yeah, you know what? We didn't do that, and I think I decided to take that. Oh, okay. So okay, thank you. I'm going to tell you. Okay, thank you. All right, folks. Let's review the next couple problems, and then I'd like to review a couple more problems before too much class time goes by. So next was number 7, and who did number 7? Jacqueline, but Jackie is not here. So I'll do number 7. So we want to graph a square root function. Now remember, your basic square root function goes up 1, right 1, up 1, right 3, up 1, right 5. So that's my basic function, but I'm going to move it right 1 and down 2. Right, so that's my transformation. Inside, I do the opposite, so I'm going right 1. Outside, I do the same, so I go down 2. And so I'm going to take my origin point and move it right 1, down 2. And then I'll draw my square root graph, which is up 1, right 1, up 1, right 3, up 1, right 5. And there's my graph. Now it does say to make a table of values to support my answer. So I'm going to specifically make a table of values using the numbers I know are on the graph, namely 1, 2, 5, and whatever that is. 1, 2, 5. That was up 1, right 5, so that would be 10. So I graph it first to see where the graph is, and that tells me what numbers I can even plug in. Like for instance, now I know my domain. My domain is anything starting at 1 moving to the right. So I could go ahead and write down my domain as from 1 to infinity. And therefore, I shouldn't bother plugging in anything to a table of values that's less than 1. And I plug in 1, 2, 5, and 10 because I know I'll get a good answer. So like this will be root 1 minus 1 minus 2, which is 0 minus 2, which is negative 2. And this will be root 2 minus 1 minus 2, which is root 1, which is 1 minus 2, negative 1. And then this would be root 5 minus 1, which is 4. Square root of 4 is 2. 2 minus 2 is 0. And then root 10 minus 1. 10 minus 1 is 9. Square root of 9 is 3. So 3 minus 2 is 1. And so that gives me a table of values which confirms each of these coordinates. My first coordinate was 1, negative 2. That was correct. My next coordinate was 2, negative 1. That was correct. My next coordinate was 5, 0. That's correct. And my last coordinate was 10, 1. And that's correct. So when I say make a table of values to support your work, your table of values is just literally going to tell you the exact same coordinates you just put on your graph by doing the graph transformation. So it's 2 ways to see the same answer. Okay, number 8 was done by Annabelle. So in number 8, she just has to solve for x. So the first thing you need to do always is isolate your radical. So she isolated the radical by subtracting off the 6, dividing off the 2, and then she had a radical so that isolated, now she can square both sides. That got the x minus 3 equals 49, and then moving over the 3, she got 52. And then you'll notice she plugged in the 52 to check to make sure that she got the right answer. Thank you, Annabelle. And then Michael, number 9, which was over here. So Michael, he didn't have to isolate his root. It was already isolated. So all he had to do was square both sides. That made the problem a little trickier because he ended up with a quadratic, x plus 11 squared. So he got a quadratic, x squared plus 22x plus 121. He then proceeded to move all of his terms to one side, which gave him x squared plus 21x plus 68. And then he noticed that he could factor that. What multiplies to make 68 that adds to make 21? 4 and 17. So he then factored it in x plus 4 and x plus 17. Using the zero product rule, he saw that x was negative 4 and negative 17. So that was phase 1, the actual algebra to generate 2 possible solutions, negative 4 and negative 17. But then he actually plugged negative 4 in, and he saw that it made a true statement. And then when he plugged in negative 17, so that would be negative 17 plus 53 equals negative 17 plus 11, he saw that he got root 49 equals negative 7. What did I do wrong? Is that 17? It is 17. What? Oh, right, that's 36. Okay, there we go. So 6 does not equal negative 6. And therefore, x equals negative 17 was not a solution. And so he had one extraneous solution. All right, thank you, Mike. Yeah, very nice. Okay, that brings us up to number 10. Austin's here, great. So let's have the next couple people come up. We'll do Austin and 1 and 2. That's Evan and Raina. Austin, Evan, and Raina, and then I might take a pause and go over a couple problems. Yeah, in fact, that's for sure what we'll do. So come on up here, Austin, Raina, and Evan. Oops. Okay. No, what was Jennifer. So you want to find the domain, and which one? Okay. Okay. So first of all, it's p of x divided by g of x, right? So it's p of x, which is 1 over root x, divided by this. So it's, oh yeah, you do number 1. Yeah. So you have 1 over root x divided by x squared minus 4. So I'm just going to come up here and divide 1 over root x. And then I divide by x squared minus 4. Right? And x squared minus 4 over x squared minus 4 over 1. Dividing by a fraction is multiplying by the reciprocal. So I really have 1 over root x times 1 over x squared minus 4. And still in parentheses. Now I can multiply straight across, and my function that I'm actually looking at is 1 over root x times x squared. Yeah. So that's the whole thing. Yeah, you can go ahead and factor that if you like. X plus 2x minus 2. Put the root x next to it so you can see visually all of it together. So now the domain exclusions, there are 3. One is that you cannot let the denominator equal 0. Another is that you cannot square root a negative. And the other is that you can't log a negative. So what we're looking at right now is saying that this whole thing can't equal 0. So that can't be 0, that can't be 0, that can't be 0. That tells me right away that x can't be, first of all, x can't be 0. And then x can't be negative 2, so negative 2 equals 0. And x can't be positive 2, because that 2 equals 0. So I know that x can't be any of those things. And that comes from the question, the denominator can't be 0. So now I have a number line that looks like this for all those things. And my number line, I know that I can't be 0, I can't be negative 2, and I can't be 2. So those are 3 open circles, 3 exclusions. Now I also know that I can only square root a positive number or a 0. Well, I know 0 is already excluded, so I can only square root a positive number, so I can only shade now the positive numbers. I'm not going to shade any negative numbers. So now I have my domain. My domain is from 0 to 2 and from 2 to 2. So you would just put that in the domain interval notation. Other way around. It's not infinity to 2. You always read from left to right. If you from 0 to 2, you go from 0 to 2, you read it left to right. Just like that, but you have a union symbol. That's it. Awesome.
So, number 11.
Yeah.
So I just multiplied 1 times 1,150 and 115. And then I have to do this, which is 2.
Well, I tell you what, this is a problem I'm about to do with everybody.
Okay.
So let me go ahead and go through the whole problem.
Well, I got it correct, is what I'm saying.
Oh,
I have to.
Yeah.
And so I have to do this, and then I just multiplied that, or divided that to find out how many years it was.
Oh,
Because
okay.
This is how much you're getting, how much you're losing per year.
But you're not always losing 115 per year.
Okay.
You lose 10% of whatever you have per year. So it's
Okay.
changing everything.
Got it.
But you're saying you ended up with the same answer? What
No,
was it?
no, it was kind of close, but this was my answer, and this was the answer to that.
Oh, okay, I see. Yeah, I see. Yeah, this is definitely the way to do it.
All right.
Okay. All right, folks. And number 10 was done by, Austin. And number 10 is down here. So the first part A, was saying that the skid mark was 209 feet. And the formula itself, feet, gets plugged into the formula. So we plugged in 209, did the root of 20 times 209, which came out to be 64. So that's great. The second part of the problem, it says they were traveling 49 miles per hour. That's miles per hour, and that's what V is equal to. So we set that equation equal to 49. And then squared both sides to get rid of the root, divided off the 20, and you got 120. Okay, thank you, Austin. And then just starting off the beginning of chapter 6, so Evan did number 1, which was quite a few problems. Thank you, Evan. So first, Evan took the log form and converted it to exponential form. That's the key skill, converting the log form to exponential form. So this is left to the right equals middle, 2 to the x equals 1/4. He knew that 2 to the negative 2 would equal 1/4, so he just said the answer was negative 2. That's something he just did in his head. If you wanted to, you could also write the 1/4 as 2 to the negative 2, because 1/4 is 2 to the negative 2. So now you have 2 to the x equals 2 to the negative 2, therefore x must be equal to negative 2. Both ways work. Okay, so then again, Evan converted this from log form to exponential form. Left to the right equals middle. 5 to the negative 2 equals m. So 5 to the negative 2 equals m. And 5 to the negative 2 is equal to 1/25, so that's what m is equal to. And then again, converting from log form to exponential form. Left to the right equals middle. 4 to the x equals 1/64. So 4 to the x equals 1/64. And again, I believe he just knew that 1/64 is 4 cubed. So 1/64 is negative 4 to the negative 3. And therefore, x is equal to negative 3. And then the last one, 10 to the what is 10,000. So that's just something you think about in your head. 10 to the what is 10,000. You can always just count the zeros, 1, 2, 3, 4. So 10 to the 4th is 10,000. Okay, thank you, Evan. And one more problem, number 2 is number 2. Oh yeah, find the domain. Great. So folks, remember there are 3 things you need to check with domain. With domain, you are not allowed to divide by 0. You are not allowed to square root a negative. And you cannot log 0 or a negative. All right, so I just wrote down 3 things you can't do in math. You cannot divide by 0, you cannot square root a negative, and you cannot log 0 or a negative. That means what you need to check for is that your denominator can't equal 0. Your radicand has to be greater than or equal to 0. And the argument in the log must be positive. So ultimately, you just take whatever's inside the log and you say it has to be greater than 0. So that's what Raina did. She did 4 plus 6x has to be greater than 0. So she just wrote down 4 plus 6x is greater than 0, solve for x, and she got negative 2/3. Therefore, on a number line, you could only start at negative 2/3 and then go to the right. And in fact, it has to be greater than negative 2/3. So that's an open circle, go to the right, and that's your domain. Okay, thank you, Raina. Thank you, everybody. Now I have just a few minutes left. I'd like to take a look at a couple problems that I just realized today, walking around to talk with you folks, that we didn't do in class. So first things first, everybody take a good look at number 15 and cross it out with furious joy. Furious joy. That makes sense, right? Cross out number 15 with furious joy. So you're crossing it out furiously and you're feeling joyful about it. That's what I mean. Okay, now 11 and 16. 16, I just realized I solved in the notes packet using a technique that we didn't use in class. So let's start by looking at 11. Because 11 was a technique that I didn't talk about in class, and now here I realize I put it on your practice test. So, in number 11, it says here that a computer purchase for $11.50 loses 10% of its value every year. So right up front, if you lose 10% per year, how much do you keep? 90%. So that's worth noting. So you lose 10%, but you keep 90%. That's important to note because we only ever do mathematics in the keep. We don't ever put the lose value into a formula. You only put the keep value into a formula. That's really important to notice. That we're never going to use the percent that you're losing in the formula. You're only ever going to use the percent that you're keeping. Now you might say, well, Mr. G, if that's the case, why do they tell me that I'm losing 10% per year? Why don't they tell me that I'm keeping 90% per year? Well, because we don't normally go around saying things like that. When you go into a store and you're like, hey, 30% off. Nobody says, hey, I only have to pay 70% of that. But wouldn't that be funny? If like every time you walk into a store, they're like, sale, 40% off. What if they said, sale, you only pay 60%? Everybody would be confused, right? So in society, we think about percent off, 20% off, 30% off. But really, you're paying 60%, you're paying 70%, you're paying 80%. So formulas, you use the keep percent. So the computer's value can be modeled by this function. So the value as a function of time is a times b to the t. Everyone write this down. A is the initial value. And b is the keep percent. And that's it. That's what you would need to know. That in this particular formula, a is the initial value, just like a naught and n naught. And b, the base of that exponential, is the keep percent, how much you're keeping. So we can go ahead and write down the formula for this right now. You start with 1150, and then how much are you keeping? 0.9. So there's our formula. And the formula makes a lot of sense because every single year that goes by, you're keeping 90% of the value. So if 3 years go by, that means you'd multiply 1150 times 0.9 times 0.9 times 0.9, and that's what that exponent is representing. How many times, how many years have gone by. All right, so there's our formula. In the exponential model, A is 1150, B is 0.9. How many years will the computer be worth half of its value? So there's 2 ways to do that. You can say, well, I'm solving for t in how many years? What's half of 1150? Is it 575? Yeah, so when will it be equal to 575? So there we go. That's what we're asking. And you're already ready to solve that. Our unknown is in the exponent, so you know you're going to use a logarithm. We divide off the 1150, and you already know what's 575 divided by 1150? Half, because that was the question we asked. When is it worth half of the value? So we have 1/2 equals 0.9t. And at this point, you can do a log. So I'm going to write 0.9t equals 1/2. So now I do log base 0.9 of 1/2 equals t, which you have to use the change of base formula. So that's log of 1/2, so that's log 0.5 divided by log 0.9. And that's how many years we'll have to go by for that thing to lose half of its value. Oh, good. So that's the end of number 11. Now you'll notice what's nice about this is that we didn't do the model of e to the kt. Because see, we could have done that. We could have done the model v of t equals the initial value times e to the kt. We could just as easily use both models. Both models will give the right answer. It's just this model is so much more user-friendly because the base is 0.9, which you obviously know what 0.9 means. That means you keep 90% of the value. If we had done this over here, oh, well, we would have had to say, we would have had to first solve for k, and then use that to come up with the half-life. So both models would work. It would just look different. So we would say the initial value is 1150, e to the kt. Oh, and do they even tell us enough information to solve for k? It loses 10% of its value every year. Oh yeah, you could do it. So so keep 90% of that. So keep 90% of that. So now I have 1035 equals 1150 of e to the k times 1. There, after 1 year, I kept 90% of my value, and then I can divide off the 1150. I'm just trying to solve for k right now. So now I have 0.9 equals e to the k. And so now I can solve for my k value. That's simply natural log base e of 0.9 equals k. So k is natural log of 9, which is 2.197. Okay, the reason I just did all that work is to show you the difference between these two models. The model that this problem suggests, I think, is user-friendly. 1150 times 0.9 to the t. And you can look at that and know exactly what you're saying. You start with a value of 1150, and you keep 90% of the value per year. Whereas when you write down this model, v of t equals 1150 e to the 2.197 t, believe it or not, these two models represent the exact same formula. And in fact, if you calculate e to the 2.197, the answer you get is 0.9. It's just that sometimes people want to use this model and sometimes people use this model. They both mean the same thing. Okay. Oh, darn it. I'm a minute over. Okay, so what does that mean? In number 16, you'll notice now in number 16, I solved that problem using the model from number 11. So if you want to use the model from number 11, you can, or you can do the model just like we did in class. Either way, when you're looking at number 16, just make sure that since it decreases by 51%, what does that mean? You kept 49%. Because we always calculate with the key percent. All right, well, if anyone has any questions, please email me throughout the week, over the weekend, come up to my office hours. Yaritza.